Donc, merci Marc d'être avec nous. Je sais pas si on t'entend pas, tu as ton micro.
Ouais, c'est bon. Merci. Vous m'entendez là?
Je pense que vous connaissez tous très bien Marc, c'est pas la peine de faire une introduction trop longue. Voilà, juste en 2 mots, ça fait très longtemps maintenant que Marc travaille sur ces techniques d'intelligence artificielle, de machine learning. Et il a très gentiment accepté de venir nous parler de beaucoup de choses, j'ai l'impression, aujourd'hui. Donc, merci beaucoup d'être avec nous, Marc, on t'écoute.
Okay, so I'll switch to English, as I understand. So thank you. So feel free to interrupt me. So this is just, I'm gonna try to, in this seminar, maybe the title is a bit too broad, but trying to show you or to make a quick review of what we have been doing with our group in the last years in trying to, understand how deep learning can be used to physics of galaxy formation, which is my main interest, and what we have learned so far, and where I think deep learning could, indeed perform well, and others places where still, some work to do and maybe not so useful. So yeah, so as I said, feel free to interrupt me whenever something is not clear. And I want to especially thank all these people that you see below, who are students and postdocs who have been working with me or are still working with me on these topics. Okay, so I think we all are, something that it's obvious in those years that something is happening in this world of artificial intelligence, when I call deep learning, I will talk about essentially neural networks. And this is just a plot of the relative change of numbers of papers in the archive mentioning some neural network. And you see that the increase is unprecedented. So the amount of papers today mentioning or using neural networks for astrophysics is growing super fast, exponentially. And this does not compare with other revolutions, for example, like the exoplanet that you can see here in light gray, which indeed created an increase of papers, but it's not comparable to that. Even Bayesian statistics, which have been steadily increasing, doesn't compare to this growth in papers. So it's clear that something is happening in the field. So these neural networks, are catching attention and making at least, an impact on the field. And so the amount of, if you look at more where is machine learning being used, it's not uniformly distributed in all the fields in astrophysics. So this is a nice visualization of papers that have been published with different topics in astrophysics from this nice website, Archive Sorter, which is being done by Brice Menard. And you can see where papers cluster with different keywords. And if you overlay here now papers using machine learning or neural networks, you see that they are not everywhere, but mostly everywhere. Essentially, I go back here, you see that the redshift, there's a big cluster of machine learning there. In here in galaxies and mass, there's also a big cluster of machine learning. And then this is data, of course, models, a little bit on cosmology over here. But there are other fields like X-ray or dust, for example, AGN, when there's little machine learning. Here in radio, for example, some of you are interested in these, started to come in, but it's not that big. So the takeaway message is that it's rising fast, not uniformly, but mostly in all fields in astrophysics. And so we're trying to understand, so what is this bringing to the field, right? So at the end, deep learning, what is it? and just to start with, and I think I like to look at it as the ultimate fitting machine. And at the end, the only thing you're doing is, which is bringing to the community, is a very generic differentiable framework, which essentially you can tune to fit or to solve almost any task. And at the end, it's a fitting machine that you can, make it more or less complex, but you are fitting a model. And by introducing this generic, framework that you can differentiate and then so you can optimize, this triggers a change of paradigm in the way we approach data processing. And this is, driving all these, bunch of tests and on different data problems. So, but at the end, it's just a fitting machine, and most of the things we do in astrophysics is fitting, right? So essentially, you have a cloud of points here, and you want to find a model that explains, a model F that explains the one quantity versus another, with depending on some parameters P. Now, when you are faced with that problem, you can choose essentially two approaches. And basically, the classic approach in astrophysics and in many fields of physics is, try to derive the parameters of Fp using your physical insight. So you know what is this a physical problem, you know what you expect, you know that there are some physics, so you plug in this physics on it, and then you try to explain the data. Of course, this is a very bad model for this, but essentially, this is what you try to do. You define your model based on some parameters, and you try to fit it to your data. Now, the other thing that you can do is, and this is what deep learning is bringing, is I don't care, or I don't know, I don't have any idea what P are, what are the physics that drives the P parameters. And so I will learn this P from the data, which is data-driven. There's no physics. I know P is not meaningful. I mean, doesn't have any physical sense, but with this generic framework, you can find a model that goes more or less through your data. And these are two complete different ways. And what deep learning is doing to the community is that we are more and more moving to this side, in the sense that let's use the data to learn the parameters instead of using more the physics. So this already tells you that it's not always useful, and depending a lot on what your problems are and what are you looking for, deep learning might be not the solution for you. But for many problems in which you don't really care about P, this is a very powerful and fast way of fitting your data. And this is in fact driving this huge amount of work, in which essentially is changing the way we process data. Now, this is, for example, for many years we have been, working on specific software to solve specific problems. And this is, I'm putting here a standard, photometric pipeline for optical or near infrared, but in many other wavebands or fields, it's the same, in which basically you get some images, you use some software to detect your objects, then you will measure some photometry or some other measurements on your objects, morphology, you will measure distances, you will measure masses, and all these things are done with different specific software for which, we use the physics and the knowledge we have on the data. And this has been developed over the years. Now this, deep learning is changing this paradigm, and we're going back to the data and just using the generic frameworks. And this is basically what we are, seeing, experiencing now. Instead of, having this specific software, what they have is the data, the pixels, and we have some, neural networks or modeling trying to extract some features. With this all generic purpose framework that you can optimize using different rules. But again, this is if you are throwing away some interpretability, some you don't know exactly what are the parameters of your model you're fitting. And so these works particularly well, and I think one of the major breakthroughs is for the classification problem. So this is a problem that is, very common in astrophysics and many physical science, and that doesn't require control of what are the parameters that your model is focusing on. And this is very simple. The classification problem is just, you're trying to put objects in boxes before any scientific analysis. You might want to detect, spiral galaxies, spheroidal galaxies. You might want to detect, stars. You might want to find cosmic rays, strong lenses. This is a step that is useful for many scientific applications. And that doesn't require knowledge of parameters. And in that particular case, deep learning excels, right? So this is an example of how well you can recover the visual morphology of a galaxy as compared to human classifiers and deep learning classifier. And you see that it's close to 100%. And just to put this in context, if you use, a more classical approach and you are trying to measure and try to control the parameters that you are measuring instead of just feeding the pixels, the contamination is way larger, even only for 2 classes. So this is really a breakthrough in which, deep learning is really accelerating science in that respect, probably solving a problem, and it's here to stay. I don't see how we cannot, use this for classification. So again, this is again a change of paradigm, and I want to just emphasize this. You're going from trying to, what we've been doing in the past, trying to, measure some parameters on objects, and then trying to find the right parameters to measure, and so with the knowledge of physics, to just getting the pixels and feeding these to a feed-forward network, right? So these are the typical now state-of-the-art, let's say, or networks that are used for classification, which are what we call feed-forward networks, and basically they are composed of several convolutional layers. And then a fully connected layer, and you can have them in many flavors. But at the end, you are just feeding the pixels in here and mapping into a classification. This is just another example of how this change of shift of paradigm is affecting all the classification. Strong lensing is clearly a field in which CNNs or deep learning has changed the field. You can see how, again, so strong lensing is about finding arcs around galaxies due to gravitational effects, and you can see that before this deep learning revolution, again, people were finding or looking for algorithms to isolate. So based on the knowledge of, I know that around an elliptical galaxy, which must be red, there must be I need to find some kind of arc shape which is blue, and so on and so forth. So you're using this physical insight to build a model that will find your lenses, right? And of course, this works in some cases, but not in all cases, and you're making some assumptions. Okay, this, of course, is being replaced by, just, again, feeding lots of images with known lenses, and then, to a neural network that will identify if it's a lens or not. And I think, so maybe, younger people in the audience don't forget that classification was a problem before. So we didn't know how to deal with, for example, Euclid data or LSST data, and how are we going to, find lenses or classify galaxies. And this, thanks to deep learning, is basically solved, which is surprising. And so maybe this is not, a revolution in the sense that we are not doing new science, or it's not artificial intelligence, making a huge discovery. But in that respect, when you use deep learning that way, it's a science accelerator, and I think this is important. So it's removing a problem and allowing people to focus on other things. And I'm taking this from a slide by Tommaso Treu talking about specifically, strong lensing science with the Raman telescope. And you can see that, when you have these challenges ahead, the first one, which is finding lenses, this is done. And this is done thanks to deep learning. So, I mean, this is an important step forward. And so this allows you, basically to focus on other things, on other challenges so in fact, you are, kind of accelerating the science that you can do. And so you can push this a bit more, and so just an extension of this classification problem. Another problem in which basically you don't care about the models, you don't care about the interpretability, is everything which is related to segmentation or detection, which at the end is, a classification at the pixel level. You're trying to get an image, and you're trying to see what, objects, or what is the object belonging, or each pixel belongs to. And these you have in astronomy, we are very familiar with these, because you have, when you get observations from the sky, you have many artifacts. You have cosmic rays, and you have contamination from stars, saturation, these kind of these kind of effects. But again, before deep learning, what you need to do here is essentially, finding algorithms to specifically detect cosmic rays, to detect spikes from stars, and so on and so forth. Now, with this generic framework, what you can do is just optimize it that way, feeding the pixels, and then you have a very powerful detector that can, classify pixel by pixel all the different artifacts or objects that you see in the image. And again, this is an example from a recent paper from Maxime Payassa, but I think this is something also that in which deep learning necessarily will stay. It's faster, more efficient, and then again you can use this generic framework to detect these objects. For example, another very difficult, or challenging scientific case in which people have been struggling a lot with is the problem of the blending, in which basically, as you go deeper and deeper, for example, this will happen with the LSST survey. You go deeper and deeper, you have lots of objects that overlap, which is, because of projection effects, you have one galaxy on top of the other. And this, when you're wanting to do, precision cosmology, for example, you want to measure lensing or weak lensing shapes of these galaxies, this creates an important bias in your measurement. So you want to deblend these objects. Again, this requires it's lots of assumptions, so you can do with parametric modeling and so on and so forth, but you can also try to address this in the same approach with machine learning, and it turns out that this is again a very efficient way of doing it. And this is a more you can again play with more complex networks. I'm not entering into detail, but essentially you can combine encoders, decoders, and then you can put here some probabilistic modeling, just to not only segment the objects, but also provide an uncertainty estimation. Okay, and this is something I'm not emphasizing much, but one of the criticisms that people might do to these neural networks is that they are black boxes, which I think mostly for now they are, but they don't measure errors, and this is changing fast. And so you can use other networks to measure the errors and provide segmentation plus an uncertainty. And again, this is, I think, somewhere where it's difficult to beat deep learning in these particular fields. This is an example of how this works, this probabilistic learning, in which you have your input image here, you have a true segmentation, and you predict them. But since you are making this probabilistic behavior, instead of having one single estimate for every segmentation possible map, you have a probability distribution, a PDF, from which you can sample. And so for a given map here, for a given stamp in the sky, you can have several realizations. So then you can compute an estimate and a dispersion, and you can measure where it's more uncertain, right? So, and just, with a single neural network. Now, however, it's important to know that when you're using these kind of techniques, you are changing the focus of your attention, but at the end, it's a fitting technique. And in order to fit, you learn on the data, which we call the training set. And so this is not magic. So you cannot learn beyond the training set. And so it's not because you have a network that is able to predict something that you are learned from the data that is useful. You are not, learning beyond what you have, put in the first place. And we see in the literature lots of, toy models, because, this is very appealing in the sense that, okay, I have the generic framework in which, basically I can put whatever I want in input, and I can try to predict whatever I want as output. And actually I minimize it if I put the right, loss function, and it provides some results. And this is an example of what I call these toy models, which are fun, but probably, you know, not very useful from a scientific point of view. These guys, this is a recent paper. We're trying, for example, to predict from images. So you have multi-wavelength images from the Sloan, so 5 bands, UGRIZ, and you're trying to use a neural network to predict a spectrum. So since in Sloan you have, you know, a fiber spectrum from the central galaxy, so you have the imaging from the spectrum. You can play this game and trying to say, okay, can I predict spectrum of a galaxy just by using its image? And actually, it works quite nicely. You can see below some examples, and in fact, in these so these are the inputs, and these are the predictions. So here, normally you see a black and red spectrum. Black is the ground truth, and red is the predicted. So you see that they overlap. You know, almost you don't see one on top of the other. So the network was fine. So it has learned, and this is, you see the power of this genetic powerful, you know, fitting technique. It's learned this mapping. However, you don't know the parameters. You don't know, you don't have any control on that. And you have learned the mapping, but are you learning some physics from that? So can you use these, would you use these to do any science? Now, would you go and take an image and then predict its spectrum and analyze its spectrum? And I mean, you are getting an average spectrum, but you're not learning anything new, right? So you're learning what you already know about the mapping between, that there's a correlation between the morphology and the color and the spectrum. So, and this is an important point. So you're not going, you know, you're not predicting the future. You're not going beyond what your training set. It's a, you know, a fitting algorithm. So to summarize this very first part, I mean, deep learning, I think it's important. It modifies the focus of attention. We are now paying attention to, you know, not finding the right models, but for some applications, you know, it's a matter of finding the right architecture and just playing with the data. And in that respect, for many applications such as classification or detection, it's an excellent science accelerator. And I think it's here to stay. There's no way we will analyze the future data coming for classification and detection without this technique. However, are we learning anything beyond our training set? Is it really, you know, besides this science accelerator, which I think it's fundamental, it's important, is really teaching us something about physics? Are we learning anything beyond our training sets, essentially? And so I think this is where maybe we should start moving forward. So, so just to put an example, so if you want, you know, if you don't have a training set, what can I do? It's just, you know, can I learn something? And this opens the door, you know, towards, you know, what we call more unsupervised learning. Now, intermediately, in between, you have, for example, what we can do, for example, for classification, and this is an example of how you can start dealing without doing things without the training set, is in astronomy you have at least, you know, and introducing now a bit of knowledge again, but on the data processing. We know, for example, in astrophysics, what are the effects of cosmological dimming on a given galaxy, when you observe a given galaxy at low redshift or high redshift. And for example, this is an effort we made in trying to classify dark energy survey galaxies, but in terms of morphology, again, it's a classification problem, but for which we didn't have any training set. So we didn't have, you know, classification of galaxies, of all DES galaxies. We have only, you know, classification from Sloan and on nearby galaxies. So basically what you can do by using the knowledge of you have on the data is trying to, you know, just simulate a galaxy for which you have a label, and then try to simulate it at high redshift or high and fainter magnitudes. So for example, you take this spiral galaxy and you simulate it for which you know a classification. This is something that the human eye can do, and there are training sets on that. And then you try to, you know, put it at higher and higher redshift. And this is how this galaxy would look like in DS at 0.3, at redshift 0.3. And the same for an elliptical galaxy. So you say these guys look very similar. And it's very difficult to build a training set based on that, because not even a human eye can do it. But you can, you know, use this simulation, use the label you have here, and expect now that this generic fitting neural network will be able to, you know, extract some features from these. And actually, it works quite fine. So if you do these, you see that these are different proxies, but essentially you can look at this plot over here. And I hope you see my cursor, in which it shows you the basically the accuracy of the classification for different magnitudes. So you see that you're nearly around 100% for classification only in 2 types, but even up to these magnitudes over here. So you see that this is 21, 21.5. Even at this stage here where the human eye doesn't see anything, you are able to get it right. And again, you're using a training set that it's built for that, using the knowledge you have on the physics. And this, for example, has allowed us to put, a morphological catalog of 27 million galaxies with basically no training set, which is something interesting. But again, now uses some knowledge. So that's why I'm saying about changing the focus. You put the knowledge of the physics in building your training set, not, in extracting the features of the model. But then, as I said, this is, again, it's the same thing. You are not learning anything new. You're just, trying to build a training set to find what you're looking for. Now, probably the next stage on this is, let the data speak, or using, what we call now self-supervised learning. And in that respect, because of this way of, processing the data with different layers, CNNs are very powerful feature extractors in the sense that they can learn from the data, and eventually they can teach us something about the data. And this is something that we can try to, push forward and trying to see if we can, learn something about what is the data telling us, instead of, just fitting the data with some labels. So the standard way of doing these is what has been now out for several years too, is with, what we call encoder-decoder networks, which come in different and lots of flavors. But essentially what you do here is, it's instead of, this linear mapping, you have this shape of, a compressing network and an expansion network. And essentially you have your input, you have your output here, which turns out to be the same. And then you're trying to, find here a representation of your data somehow. This is a particular implementation, which is called the VQVAE, but there are, different variants. And the idea is more or less the same, in which essentially, you compress your data. You use your network to compress your data. And by doing this data compression, you obtain a representation of your data. And from that, you can learn something. For example, and then if you apply these to, for example, the same problem of galaxy morphology, then what happens is you obtain how are the morphologies without any label of galaxies seen by an unsupervised neural network. And you see that, so these are different groups that have been done a posteriori, but you obtain, like, depending on the way you use it, like 27 different morphological groups that, is what the network has understood that should be in different boxes. And you see there's, of course, a kind of trend here. You see, typical elliptical galaxies over here, more spirals over here, clumpy galaxies over here. And this is where you reach this problem about, okay, I have a great fitting machine, but I don't know how to interpret it. And the interpretation of these different groups is very difficult. Why is this galaxy over here different than that one? What is making the network taking this decision? This, we don't know how to do it yet. And this is, I think, a very, potential, maybe an excellent way of making progress on this field, is trying to learn what are the networks, what are these networks telling us about the data. So for now, the only thing what we can do is, compress it, find groups, and try to understand what are these groups. But we cannot ask the network, why did you put this here and this, that here? And once if we manage to get that point, maybe we'll be a point in which these networks are teaching something about the physics that we didn't know. We are not there yet. What we can do is, then find correlations with known physical parameters. For example, you can take these 27 classes that we found there and trying to see how they correlate with color, for example. And then you find out, and magnitude here, absolute magnitude, you find known correlations. You have that some clusters here are red and bright objects, others are blue and more faint objects. So, you know, it's using this information that we knew, but why is this split in 3? This is very difficult to know. And then you need to interrogation techniques, but even the interrogation techniques of the networks that we have are very rudimentary today. So they don't tell you anything about the physics or anything. They are telling you what pixels are important or in the image. And so in that respect, it's extremely difficult, you know, to learn something from them. So I told you about this, you know, classic way of, of compressing the data with encoders. People are now starting to use also now, it's becoming very popular, something that in the same idea of learning representations and trying to get rid of training sets is contrastive learning, what we call contrastive learning. And the idea here is a bit different. So this is something that it's an ongoing work in which we are trying to see if we can, you know, learn something about manga maps. So manga, you know, is this IFU survey of Sloan galaxies. And in which you have, you know, for every galaxy in Sloan, you have multiple fibers, and then you get a map. So you get both spectroscopy at the pixel level and imaging. So we're trying to see if, you know, with this more complex data, which becomes difficult to visualize. So can we use deep learning essentially to, you know, find the structures in this data, even if you don't know anything about the data. So the way you are doing this is with contrastive learning. We're building some maps here. I'm not entering much in the details, but I can answer questions if you want. This is still ongoing work. But the way this contrastive learning work, I find it interesting, is you take a map here, an image, and what you do is you will, you know, apply some perturbations to your image, which you think shouldn't change the representation of this image. This is again where you put your knowledge of physics. You can say, okay, a galaxy, this is zoomed out or zoom in should be the same, or if it's rotated should be the same, and so on and so forth. And then you have these neural networks, and then you have other galaxies which are not the same. And so you want that this neural network with just, you know, a function that learns some representations, and then you transform this image into a series of numbers here. And you want that, you know, these numbers you extract from these different views of the same galaxy should be very similar. Okay, so if you change this image, I'd want that these numbers are very similar. So the representation I learned from that particular image should be very similar. However, in another galaxy, which is different from that one, I want these to be different. And that's why you start, you know, learning some representations. And the good thing here is that you can, you know, apply here all the transformations you want to get rid of undesirable, you know, non-physical correlation. For example, in manga, what happens is that some objects are viewed with sampled with a lot of IFUs, other with less IFUs. And if you don't do anything, this is the main effect that you will see, right? So this you can, you know, teach the network to remove these effects. And if you do that, for example, this is a visualization in 2 dimensions of what are the features learned by contrastive learning of all manga maps. And you see that if you don't apply any contrastive learning, you just, you know, throw the pixels and try in lower dimensions, see what happens. You see that what basically you see here, this is in the top left corner, what you see here is the sizes of the IFU. So basically, the first thing a dummy, you know, data compressor will see are the sizes of the IFU. Of course, you don't want that. This is not any physics. However, when you use the contrastive learning, you see that it doesn't depend anymore on the IFU size because you force that, okay, by introducing some knowledge. And then you can start, you know, seeing that it starts correlating with more physical parameters. For example, the velocity dispersion. You see that galaxies with high velocity dispersions are here, galaxies with low velocity dispersions are over here. But again, it's difficult to interpret, but it's a way of visualizing your data in higher dimensions. I think it is something that for which deep learning should start helping as data become more and more complex. And then using the same idea, then you can a posteriori look for the different parameters that best correlate with the different groups. So what is trying to understand what is the network learning. But again, this is very rudimentary. But essentially, you can see that if you divide these now representations in 3 groups, this is just focus on that one top left. This is the main sequence, stellar mass and star formation rate. And you see that naturally, the network has found that there are some galaxies which are rotators and star forming. It finds the main sequence here in red. It finds that there are slow rotators here, so very quenched galaxies, massive, with very high velocity dispersion. And it finds these intermediate, green valley quenched galaxies, which are rotations, which do have rotation, but they don't have star formation and they rotate a bit slower. So naturally, without knowing anything about the physics, you let the data speak and you start, finding that there are these different groups. So if you knew nothing about galaxies, by using these exploration techniques and letting the data speak, you can start finding or different groups. Now you don't know exactly. Now you are applying here a lot of physics that so this is the problem. So this is where still we are not there yet, in which the network is telling you why I'm finding this group because of this. This is still where the human interaction is needed. So moving forward on this idea of letting the data speak, and so how do we make discoveries, and can we have this AI enabling discoveries? And of course, when you're starting doing this data representation, you are and letting people explore the data, you are in somehow enabling discoveries. But can we really prove that we can make discoveries with AI? So as far as I know, this hasn't happened yet, and we don't have any pure AI discovery. And I don't know if probably this is a matter of time. I don't know, but if you think about it, so I think I'm trying to convince you that most of the data processing, at least, will be done with these ML methods of the new data, which is coming, and how do we detect then these unknown unknowns where interesting science will be found? And I think the way forward, as I try to tell you, is by letting the data speak and finding representations there. The reason why it hasn't happened yet is maybe because we don't have yet this completely new data and large data set to explore. But it's maybe something that can happen in the coming future. Now, how this can be done, and specifically targeting discoveries. And this is a field which, again, I think is very interesting, which is all the field of anomaly or outlier detection in machine learning, which is also, a hot topic. And I think it's another thing that can bring, novelty, let's say, to our field. So this is so essentially what you're trying to do is find objects which are anomalous as compared to your normal data. And in order without any knowledge. So again, what would be an anomaly then? If you assume that your data is following a probability distribution, let's say P, you have your pixels over here and or your survey, your data, and it follows a probability distribution somehow. Which includes your data selection and other aspects. An object is anomalous if the probability of observing a given object is smaller than a given epsilon, so it's very small. Now, okay, this is obvious, but basically this means that you need to learn P. You need to learn what is the probability distribution of your data. And again, this is not trivial because you have a selection effect, you have the pixels, you have different wavelengths, and this is not trivial. However, you can use machine learning to learn P, okay, in the same way by learning a representation. And if you learn P, then you can sample and ask what is the probability of a given object. And you can, pre-select objects which have low probabilities, and then you can explore them. So again, is a way of, filtering out uninteresting objects. And the way you do that is what we call generative modeling. And these generative models do precisely that, in the sense that you have some data and they learn a probability density function from the data itself. So again, is the idea of completely data driven, and you learn from the data a probability distribution. So within these, generative models, you have what I already told you about VAEs, but you have GANs, you have regressive models, and these networks, what they do is, precisely given some data, trying to estimate a probability and density function. Why would you do that? Because, when you learn the probability function or density function of your data, then you can sample, and then you can produce data which come from the same probability distribution. So these are examples which most of you might know, in which, state-of-the-art generative modeling, in which basically you have learned the probability distribution from examples, and then you're able to sample and produce mock images like those. So those images are, generated only by the neural network, which has learned the probability distribution. And now you see that these achieving extremely nice details and very realistic. So it means that these are, capturing very well or learning very well the probability density function. So once you learn the probability, then you can play this game of asking if a data is, normal or abnormal, and trying to find interesting objects in your data. And this is an example of something we've done tested with the Hyper Subprime Cam, which is, this survey with the Subaru telescope, which is kind of a precursor for LSST, but with and in 1400 square degrees. And essentially what we have done here is trying to see if we can find, by using this technique, find interesting objects in this data. And so the idea is you train a generative model over here with some objects, and this allows you to learn this probability distribution, right, from the generative modeling. And once you have this probability distribution, then you can go and select an individual detection in that particular field, and probe and ask what is the probability to observe these objects from what I've learned of the global distribution of the data. And this allows you to identify the most unlikely objects that you can then look at. So this is an example of how you learn this probability distribution. So these are real HSC data, and this is what the GAN has learned. So these are mock galaxies learned by the generative model. And then, so basically, once you have learned this PDF, you can just, for every object in your survey, you can test how well it's reproduced, or how likely it is. I'm not entering into details of that, but basically you can take a galaxy which is real, ask the model to reproduce it, and then compute a kind of residual with some other parameters. And the larger is the residual, is the most unlikely it is, because it's, the model cannot reproduce it somehow. And then you can produce what we call an anomaly score, in which you have on one side what we call boring objects. I think these are very normal objects, nothing to look at. You're pretty sure that they don't contain anything interesting. And then you have the large tails of this distribution, which would be, the anomalous objects. And this allows, again, it's AI enabling or helping to make discoveries somehow in otherwise very large data. And you can then explore what will be, the normal objects, which would be those ones. You can probe for 1 sigma objects, 3 sigma objects, and you see that, you start seeing very weird objects, and most of them are, pipeline errors, and of course, but you see that you're picking up what would be strange objects. Now, the next question would be, okay, now I have this filter here, I've had this, but how I filter out interesting anomalies, right? How I find objects that are scientifically meaningful. And this is again where, since you cannot ask the network why this is anomalous or not, then you cannot tell the network ask the network to tell you, okay, this is anomalous because this, so therefore this is potentially interesting. You need, to do it a posteriori in a manual fashion. And again, this is something that, maybe the next progress comes from there, but we are not able to interrogate the networks properly. So you can use another layer of machine learning eventually to find interesting anomalies by compressing this data space of residual images and finding which ones would be more interesting. I'm not entering into details because I've run out of time, but essentially at the end you can use this anomaly score to filter out objects that are potentially not interesting, and then provide a tool to the community to look for, explore manually what are the interesting objects in here. So you can have a look at this web page in which we have put, all the anomalous objects from this HSC survey, in which, then you can manually explore and find what would be the most interesting and how they are clustered in different regions. These is two examples of things that we found. So, for example, we found these, very bluish interacting dwarf galaxy, which was found by the network, and we turned out that a group just before us had found it and was already following up. But it's an interesting object per se that was discovered by the AI. And we also found, the network found a lot of objects which were, like this one, which, you have a red object with a blue dot of centered. And when you, for example, for a particular object, we had some HST imaging, and you see that it's a weird galaxy with some perturbation here and something over here. And we are following them up with Keck, but, it looks like it could be an off-centered AGN. Anyway, so I think I probably I'm out of time. So I had a last thing I wanted to address, but I might stop here. I don't know.
I think you can continue, Marc.
For 5 minutes. Okay. So the last I've been talking about, how can we move forward? What would be, I think, the interesting things and the different achievements. And so one thing I've been playing with a lot is, which at the end goes back to classification with another point of view, is what I have been calling physics-based classifications. And the idea here is to try to, most of the classification we do, or the separation of the data we do, is based on empirical knowledge. But since these networks are very useful to extract features even beyond the human eye, and one thing we have in astrophysics is that the only thing that we can do to understand the universe is by simulating it, essentially. Once we make some observations, we try to interpret them, but then we go to simulations to see if this matches. And so can we use this deep learning to improve this link we have between simulations and observations? And we have been playing with these in the last years. And since this is happening, because as you know, we are making more and more progress on cosmological simulations, and now we are able to capture somehow the time evolution of galaxies, so that we cannot do in observations, of course. And simulations are becoming more and more successful at reproducing several statistical quantities of galaxies. So with this is an example of the recent TNG simulation, but there are several in the market. And essentially now, I mean, they are not perfect, of course. There's lots of subgrid physics here, but you have, they are reasonably well at reproducing many galactic properties. And with the advantage here is that you have a movie of a given galaxy. You can go back in time and follow the evolution of a given galaxy, while in the observation, you have only a snapshot. So, and I think, you have this appealing, problem in which, that might be suitable for machine learning, in which you have a movie of a galaxy evolving, you have a snapshot here, and can we use deep learning, to learn something about the movie and then tell you something about the snapshot, what's the evolutionary stage of a particular galaxy, which at the end is what you want to do, right? You want to have a galaxy and you want to know how is it formed. So this is, there are lots of caveats there, but something that I've been playing with in the last years. And I just wanted to show you maybe one example. One obvious example for this is galaxy mergers, of course, in which basically, galaxy mergers, we know it's a dynamic process. Things collide, and we know it's happening in the universe. But, even it's something extremely old, we still struggle to identify mergers in the data. We still don't know exactly what's the merger rate in the universe, so what's the time at which galaxies merge. And this is because it's extremely challenging when you detect an image or we detect a merger to know exactly what's the stage of this merger, for example. No? Yeah, you detect these objects here. Sorry, I'm keeping stopping the movie, but and normally, you know, this is a dynamic process, and you will observe an object here. But knowing that exactly in what dynamical process or dynamic stage it is extremely difficult. You know, to compare to different simulations and see what would be the stage of that particular observation, right? So this is typically a problem that we have in which you observe an object, we have a snapshot, but you don't know exactly in which stage it is, right? And the way you do it traditionally is, you know, maybe you can do some dynamical modeling and trying to see how best you fit observations of a given object. But doing this statistically is extremely complex. And so eventually you can use, if you have lots of examples, you can eventually convert this into a data-driven problem in which, you know, you throw a lots of examples to a neural network so that it learns how a merger works. And then it can tell you directly from an image in which likely stage it is, right? And this is a game we played with people at DeepMind in Google, in which, you know, we took this simulation from this Horizon EGN simulation that is led at the IAP, and we generated lots of, you know, hundreds of thousands of mergers examples from the simulation. So we detected a true simulation that a true merger that we know it happens in the simulation because we have the full history, and then at a given snapshot, we follow that merger back in time and forward in time, as you can see here. So as the two objects approach it, and then as they, you know, collide. And we mock these in different filters with the HST resolution and different projections. So for sets of merger, we generated, you know, hundreds of thousands, even millions of images of mergers looked from different points of view, different times, and so on and so forth. And we checked if, you know, the neural network is able to learn something. I mean, this is complex because, you know, it's a cosmological simulation. So you can have a merger coming from any direction. Galaxies might be star forming, not star forming, low mass, high mass at different redshifts. So this is lots of different possibilities, but we asked the network if, you know, it's able to learn something about the physics of mergers. So by just trying to see, if I show you all these examples and then I show you just one snapshot, can you tell me what's the merger state? What's the time since or before the, you know, closest approach? Let's say here T0. And you see that, you know, it works. I mean, it's surprisingly good in the sense that, you know, just given an image, this is that, you know, from the simulation to ground truth time, you are able to predict more or less how long, what's the time elapsed since the, you know, closest approach, so perigee closest approach, or or how much time you need to go to this perigee passage. And this is only, you know, with, you know, showing examples. Without any dynamical modeling. Of course, this is extremely fast. And then you can think about, you know, okay, now you can apply this statistically and, you know, trying to infer the times of the different mergers. And so somehow you are putting some temporal information on a fixed snapshot. We have played the same game with other physical processes, and this is still an investigation, but I think I will skip it because for the sake of time, but I'm happy to answer questions regarding these. And I think I'll jump straight to the conclusion. Sorry, I have too much material. But I think the last thing I wanted to, when you try to, learn from theory and try to match it to observations, of course, you have the problem that theory is not perfect, and that you might introduce some biases. Again, everything is on your training set. You are not learning beyond your training set. But you can use, again, unsupervised learning to see how well things match and identify objects that, follow the same region in the space. I think I will skip that, but I'm happy to answer questions regarding that. And I think I'll jump to my conclusions. So I think machine learning is somehow providing a revolution in the field of in astrophysics in general. You've seen the number of papers, and I think it's made a major breakthrough in classification. It's probably solving the problem. And again, this is not, it doesn't seem extraordinary, but it's an important science accelerator. And for that, it will stay. I think it will, of course, will be part of analysis pipelines of future big data surveys. And there's no way we can do, classification or even detection without these now. I don't think it makes sense. Of course, the bottleneck of supervised learning are training sets. And you are not learning anything beyond your training set. And you can, use simulations, use physics of knowledge, to extrapolate to other sets. But at the end, it's a supervised approach. I think future, comes in. I mean, it's interesting to, the future probably will come from self-supervised learning. I put here classification, but it's learning in general. It's still less developed, but I think this is where the focus should be put now. It can be useful for automatic discoveries. It can be useful, for data exploration. And if we manage to get, to reach a point in which we can improve the interpretability of our networks, combined with unsupervised classification, then we can start learning something new about the data. Thank you. I'll stop sharing now, and I'll take questions if you guys have one.
Thank you, Marc. So are there any questions for Marc? Well, I have a question about, I mean, you talked about a lot about 2D images. You know that we are very interested in the in IFU data and more dimensions. What is the state of the art in this domain? I mean, do you know more exploration of data cubes?
Yeah, so I explored. I'll show you an example of. We are exploring also manga data.
Mm-hmm.
So we have not tried to explore. I mean, on paper, it's not very different because at the end, as I said, this is a very generic fitting machine. So IFU data is just an image with lots of channels.
Mm-hmm.
Right? So you can, and at the end is just, you can use the same framework. It's true that, going at the regime of thousands of channels, if you have several wavelengths, it might be challenging for convergence, might be challenged, to extract features and so on and so forth. But, the framework, depending on what you do, could be very similar. And so what we have tried here in manga is, using already post-processed quantities, not the spectra directly. So using, velocity maps, mass maps, and so on and so forth. So already post-processed quantities, but we've gone to, 6 or even 10 channels, and we are learning meaningful representations. So I think, it's perfectly, I mean, I don't know. I think it can be used, for IFU without any problem.
If I understood correctly, you use those images independently, no?
No, they are fed all together.
Well, but do you, is there any correlation between the two? I mean, is it a 3D convolution, or is it,
Well, you treat them as a, as a channel of the same image. So in some sense, you do a convolution across channels as you do on standard machine learning, CNN. So you take your data cube, and then you do a convolution that goes across the channel. Yeah, I don't know if that answers.
Any other questions? Everybody's very shy.
I mean, I'm happy to take questions afterwards if you guys have any other.
Oh, yeah. Okay, so let's thank Marc and close this this seminar. And those of you who would like to stay and ask questions to Marc, can leave open the Zoom for a few minutes more. Okay, so thank you all for your participation.
Thank you all for the invitation.